Welcome to everybody for this main lecture. And I'm very pleased to introduce you Professor James Robinson, who is professor of mathematics at the University of Warwick and fellowship leader at the EPSRC, the Engineering and Physical Science Research Council. Some of the research interests of Professor Robinson are, among others, rigorous fluid dynamics and turbulence, infinite dimensional dynamical system, random dynamical system, non-autonomous dynamical system, and embeddings of finite dimensional sets into Euclidean spaces. Today, Professor Robinson is talking about some simple PDEs with surprising behavior.
Thank you. So, thank you very much for the invitation. I think it's the first time I've been invited somewhere. The main criterion seems to be that I'm not young. But I just have to accept that these days, I suppose. It's very nice to be here. And I'm going to talk about some not so simple and then some much simpler PDEs with what to me anyway was surprising behavior. And this was joint work, first of all, sorry, I can't handle these pointers, with Mikołaj Shishenga, who was a PhD student of mine and is now a postdoc, and then with Rod Laister from UWE, which is in Bristol. So it's really a kind of story part of the talk, which is how we got into looking at the problems that we were looking at, and then the solution of what we were trying to do. So I was going to talk about the Euler and Navier-Stokes equations. Here they are. As the sort of main topic of the talk, I'm not now. I'm going to talk about these much simpler systems. But really my interest in these came from some problems with the Euler and Navier-Stokes equations that I'm going to talk about for a couple of slides. So essentially the question is, if I knew something about the Euler equations, so that's these fluid equations without viscosity, then what can I say about the solutions of the Navier-Stokes equations when I put the viscosity in? And the heuristic idea is viscosity makes everything nicer, so if I knew everything about the Euler equations, I'd automatically know everything about Navier-Stokes. The problem is, there's a phenomenon and a nice example due to Weinberger of a system of coupled ODEs, so if you forget the red terms, you can have a system of coupled ODEs where the solutions exist for all time and are very nicely behaved, and then when you add diffusion, the solutions blow up. And I'm going to give you a sketch of his argument as to why that happens. So this intuitive idea that you add diffusion and everything becomes nicer isn't always the case. So wanting to understand Euler and Navier-Stokes, we then looked at this and maybe wanted to understand this. This seemed too hard as well. So we thought we'd look at the problem in a simpler situation of a one-dimensional scalar ODE and PDE. So the idea is to start off with an ODE. This is the work with Mikołaj and Rod that I'm going to talk about sort of in the second half. So I'm going to start off with an ODE where we can guarantee that the solutions exist for all time. I'm then going to introduce some spatial dependence, so make this kind of toy PDE without any derivatives in space, but with some dependence on x, and examine the behavior of this thing. And then I'm going to look at the parabolic PDE, putting the diffusion back in. And the surprising behavior essentially is you can find Fs where this ODE has solutions that exist for all time. Once you introduce spatial dependence, the solutions can actually blow up. And in certain ranges, even when you add in this Laplacian and you have some diffusion, the solutions can still blow up immediately. So even though for the ODE the solutions exist for all time and are nice, this PDE has solutions that blow up straight away. So let's start off with the Euler and Navier-Stokes equations, really just to motivate what's going on. So these are the Euler equations, and in this formulation they look really quite innocent. This is the convective derivative, so you're following the velocity of the fluid as it gets advected by the fluid itself. And this looks like a pretty harmless, almost kind of linear equation. So let me be a bit more honest and expand out this convective time derivative, and this gives you a quadratic term in U with some spatial derivatives. So writing it like this, it's not really clear whether you'd expect the solutions to exist and carry on being nice or do something nasty. Well, what we do know, and this is just some basic inequalities, if you take the inner product with U in some appropriate Sobolev space of high enough order, exactly what this means doesn't really matter too much, then we get this differential inequality for the norm of U in this space. So let's say S is 3, you can basically control all the third derivatives squared by all the third derivatives cubed. So this is like, well, this is basically d by dt of x squared is less than the constant times x cubed, and that ODE will blow up in finite time. So in terms of bounds on the solution, you get this upper bound on the solution, and it guarantees existence for a short time if you start with smooth enough initial data. And more or less, that's about all we know about the Euler equations, with some much more. I mean, you can have much more technical conditions on exactly which spaces you have to be to get local existence and blah, 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 but basically, this is what we know about the Euler equations, short time existence for sufficiently smooth data. And why might you expect something more nasty to happen? Well, if you write the equation for the vorticity, which is the curl of U, so basically just some derivatives of U, you get omega t plus u dot gradient omega, which is just transporting the vorticity around with the velocity. And on the right-hand side, you get omega dot gradient u. So this is derivatives of u. This is derivatives of u. So this is something like the time derivative of omega looks like omega squared. So if that was an ODE and it was x dot equals x squared, the solutions of this would blow up in finite time. And it's an open question as to what actually happens with the solutions of the Euler equation. And depending on who you talk to, essentially you can look at this and say, well, of course they blow up in finite time, but no one's been able to prove it. Or you could say, oh, there's lots of interesting geometric constraints and structures in the Euler equations that maybe they don't. And it's probably about 50-50, depending on who you talk to, that will tell you whether or not they blow up or whether or not they expect they blow up. So these are the Euler equations. You don't win $1 million for doing anything with the Euler equations, but you can win $1 million for doing something with the Navier-Stokes equations. And all being well, they're easier because they've got this viscosity, and so viscosity has the Laplacian in, and this is diffusion, and everything should be nicer. So what can we say about the Navier-Stokes equations in comparison to the Euler equations? Well, we have short time existence if the initial data is smooth. So if we do the same stuff as we did for the Euler equations, you take some estimates in appropriate Sobolev spaces, blah, 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 you get this kind of differential inequality. So before, for the Euler equations without viscosity, this norm squared was bounded by the norm cubed, which gives you a bound for a short amount of time and possible blow-up. But now, because we've got the viscosity in, we get an extra factor sitting in here, which is essentially minus a constant times the viscosity. And that tells us that if the data is initially sufficiently small, so if this norm in H3 is less than nu lambda, this right-hand side is negative, the norm in H3 can't increase, so it stays finite for all time. So, and then this really is doing a lot of people an awful lot of injustice. Essentially, that's all we know about the 3D Navier-Stokes equations. You have existence for all time for small data and local existence for large data. But here the estimates are somehow better because of the viscous term. So a natural question to ask, perhaps, is suppose you know that the Euler equations are regular. So either that someone has done a fantastic proof and has finally proved that all solutions of the Euler equations stay regular for all time, or you've had a vision and you're convinced that the Euler equations are regular. So you want to say, this is something I know, what can I deduce about the Navier-Stokes equation? And so the intuition would be the Euler equations should be harder because there's no diffusion. So let's assume that the Euler equations generate nice solutions. Can we say something about solutions of the Navier-Stokes equation? And the surprising thing is, at the moment, this question is still open. So what we do know is a result due to Peter Constantin from the mid-80s, which is written here. So the maths is kind of a bit too much in a way. Essentially, the moral of it is, you take a sufficiently smooth initial condition, and you assume that the Euler equations have a nice solution on some time interval. Then so do the Navier-Stokes equations, but only if the viscosity is sufficiently small. So this is kind of very strange. So the viscosity should make things nicer. So if the viscosity is small, you've got a tiny bit of diffusion. And this result says, okay, a tiny bit of diffusion, and you're still okay. But if you crank up the diffusion, and things should get nicer and nicer, at some point you can't say anything anymore about whether or not the solutions are nice. And the reason is that the proof doesn't actually use the diffusion in any positive way at all. So in the proof, which I'll show you in just a quick sketch, the diffusion's an enemy, and you can control it when it's small. So this is a strange kind of perturbation result, and it's not using the fact that diffusion should be nice in any way. So you write down the Euler equations for U. You know that this has a solution, and it's nice. That's your assumption. You write down the Navier-Stokes equations for Z, and then you write down the equation for their difference. So if you can show that the difference stays finite, you know that U is nice, so then Z must be nice, because Z is W plus U. So you want to control the difference. You know that U is nice. You don't know anything about Z, so you subtract the two equations, and wherever you see Z, you write U plus W, because you know about U and W you want to control. Well, you get an equation here, which is basically looks like Navier-Stokes with some extra terms, because pi is the difference of the pressures, and you do some estimates, like we did before, and you get something fairly similar. You control a norm squared by a norm cubed, plus a little bit of junk here and here, which you'd rather you didn't have. So W is initially 0. So what's the problem? Proving a bound on this solutions of this equation. If you didn't have this term, and you didn't have this term, W would stay 0. So essentially, if you can make this coefficient small, and this term sufficiently small, then W stays bounded. And that's essentially when you make this thing small by assuming that nu is small. So it's a perturbation argument where the viscosity is your enemy, and you're just making the viscosity small. So the question as to what actually happens if you knew about Euler and you switch to Navier-Stokes, we still don't know the answer. So why might it not be entirely trivial? Well, because it seems hard to do, but what's one kind of theoretical problem? And it's this phenomenon of diffusion-induced blow-up, which in its most elegant form is due to Weinberger in just before the turn of the millennium. So here's a set of coupled ODEs, and these ODEs have global existence. So it's very easy to see, because if you look at the rate of change of this product of 1 plus u and 1 plus v, it's 0. So what do the solutions do? They move on these hyperbolae, and if you're above this diagonal line, you go up, and if you're below the diagonal line, you go down. So if you're up here, then u goes to 0. No, sorry, if you're up here, yes. U goes to 0, and you go to here, and if you're below, v goes to 0, and you go down to there. Now, essentially, what happens when you add diffusion is we can construct an initial condition. So imagine that at your initial time, u is a little bit less than v. So you're going to go up one of these lines and hit here. Now, what the diffusion does is kind of average things a bit, and it forces u to be a little bit different from 0. So it pushes you off to the right. And then you're on another one of these trajectories, and you go up. And the diffusion doesn't let you be 0 because you're averaging, so you get pushed out, and you go up again, and you just keep kind of climbing up this axis. So the ODE would just stop, and the diffusion somehow, although it smooths things out, keeps nudging you over, and you just go off to infinity. And it happens in such a way that it goes off to infinity in a finite time. So I've got 3 proofs of this. This is proof by graph and pointer. Now it's kind of proof by hand waving, which is a little bit more convincing. And then there's analytical proof, but obviously I've missed out almost all the steps. So this, I mean, the third proof you can actually make rigorous. So now I'm going to look at the system with diffusion on an interval with Neumann boundary conditions, and the fact that the boundary conditions at Neumann is important. So it's not really clear how robust this phenomenon is for different kinds of boundary conditions. So roughly the idea is this. I'm going to take an initial condition, which is basically near the origin is c squared, and on one side of x equals 0, then u is a little bit bigger than v, and on the other side of the origin, u is a little bit less than v. So if you're positive, and it's basically c squared. So when x is less than 0, one of the terms goes to 0 and the other goes to this quantity L of x. And when x is greater than 0, it kind of swaps around, because this was the phase portrait. If you're bigger, you go up, and if you're smaller, you go down. And the thing you tend to, well, near zero, it's basically c squared, this initial data, and you basically tend to something that looks like c to the 4 as you go up this parabola. So if you're just solving the ODE, and if the kind of hand-wavy thing is that the dissipation doesn't have much effect on a time of order 1 over epsilon, because there's a tiny epsilon here, so you don't feel it for a while, you just solve the ODE, you go up one of these hyperbolae, and basically the value is c to the 4. But then the diffusion kicks in, and it averages u and v near 0, so basically you end up with the average of 0 and c to the 4. So you get something that looks like c to the 4th over 2. The order of u and v is preserved by the evolution, that's just the use of the maximum principle. So at some time of order 1 over epsilon, we've done this, the diffusion kicks in, and now we've got new initial conditions. On one side, u is slightly bigger than v. On the other side, v is slightly less than u, but now rather than having c squared, we've basically got c to the 4th. So now let's run this procedure again, and we'll get c to the 8th, and so on and so on, so the solution is going to blow up. And if you get some acceleration, depending on the difference between u and v, then it might sort of accelerate and blow up in finite time, and it does. The argument that convinces me most, to be honest, is this one. So this is the hand-wavy version, and here's the rigorous argument due to Souple some 8 years later. It's a kind of distillation of what's in Weinberger's paper. And obviously it's very sketchy, but essentially he says, let's look at the sum of u and v, and you can write down a fairly simple PDE for that. And if you do that, a little bit of manipulation tells you that the maximum of u and v is always greater than or equal to 1 if you choose your initial data properly. If you look at an equation for the difference, which is this, if the minimum of u and v is greater than or equal to 1, then you can forget this u v term here. 2 plus u plus v, u and v are positive, so this is certainly greater than the difference of u and v. So the equation for w looks like this. So now I'm going to wave my hands again a bit. So we've got, if the minimum of u and v is greater than or equal to 1, w satisfies this equation, and essentially this is w dot is greater than or equal to w squared, so you expect w to blow up. That's the difference of two positive solutions, so one of those positive solutions must blow up in finite time. Well, what if the minimum of u and v is less than or equal to 1? Well, if the minimum of u and v is less than or equal to 1, and the maximum is greater than or equal to 1, they must have a point where ut is equal to 1. So I'm going to look at this funny variable z, which is the log of 1 plus u over 2, and there's a point where z is 0. If u is 1, then this is log of 1, which is 0. So I'm going to write down a differential equation for this funny function of u, that's z. And if I look at psi is the integral of z, I end up with this inequality for psi. And if you know that z has somewhere where it's 0, you can bound psi squared, which is the integral of z squared, by a constant times the integral of the derivative of z squared. So you get some kind of Poincaré inequality for z if you know there's somewhere where it's 0. So if you put that together, this psi satisfies this kind of ODE, and this thing blows up in finite time, and that's blow up of u in finite time. So if you knew for all time that the minimum of u and v was greater than or equal to 1, you get blow up of w. If you knew for all time that the minimum of u and v was less than or equal to 1, you get blow up of u. And with some finessing, because this isn't always true, and this might not always be true, you can put these together and show that the solutions really do blow up. So we wanted to try and understand that, and this is where McCullough started at the beginning of his thesis. What really is the mechanism behind this diffusion-induced blow-up? And in the end, we found that was too difficult for us to understand, so we thought we'd look at something much simpler, and these are the simple kind of PDEs of my type. So let's look at the easiest kind of problem. We're going to look at a one-dimensional scalar ODE, which is here, and with positive initial data. So I want an ODE where I know that the solutions are nice. I'm going to take an f that's locally Lipschitz, that'll give me uniqueness. I'm going to take f to be positive for u positive and non-decreasing in u. So if f's bounded, the solutions exist for all time. Nothing I can't kind of play with things to get anything very bad to happen. So there's two possibilities for solutions of this ODE. Either the solutions tend to infinity as t goes to infinity, but are bounded for all finite time, so then I get global existence, or the solutions blow up in finite time. And there's a necessary and sufficient condition for this, derived by Osgood. So if you work out the time it takes to get from an initial condition to some y, you can just solve this equation that way, and it's this. So the time it takes is the integral from u0 to y of 1 over f. So if you want it to take an infinite amount of time to get to infinity, well, you want the integral up to infinity of 1 over f to be equal to infinity. And that's this Osgood condition. So recall my f is positive. It's strictly increasing, so it has no zeros for s positive. So if you have this integral from 1 to infinity of 1 over f infinite, all the solutions of this ODE exist for all time and gently meander off to infinity. Right? So this is the time it takes to go from x equals 1 to x equals infinity. And it's infinite. So it basically tells you in some sense that f can't grow too fast. Because if f grew very quickly, then this integrand would be small and it would become integral. So what we want to do is look at what happens in the transition from this ODE to the PDE that has spatial dependence and a minus Laplacian of u to smooth things out. So there's actually two effects here. There's an effect of introducing spatial dependence, and then there's an effect of introducing diffusion. So this is the ODE with global existence, and then we're going to look at this toy PDE, and it's a toy because it's actually not really a PDE at all. It's an ODE with a spatial dependence. So at each point we can specify initial data, but then we evolve it according to the ODE. So there's no, I mean, it's a very kind of poor sort of PDE. So because the solutions of this PDE are entirely determined by the solutions of the ODE. So if the ODE has global existence, and if we start with bounded data for this toy PDE, then everything's going to be fine. So what we're going to do is look at this toy PDE for initial data that only has to be integrable. So in some LP. So we can allow singularities like mod x to the minus alpha, where alpha is sufficiently small to make us integrable. And that's what we're going to look at. And what you find is it's relatively simple to show you can have instantaneous blow-up for this toy PDE if you take initial data that's not bounded. And then we're going to look at the same kinds of f's. So we're going to construct a particular class of nasty f's that satisfy this Osgood condition, but still increase quickly enough that the toy PDE can blow up. And then we ask, what happens if we introduce diffusion? And what we're going to see is that for some ranges of nastiness, the diffusion is enough to make the solutions nice. But if the f is nasty enough, then it's still possible to have instantaneous blow-up for initial data in LP. So this all relies on this construction of some bad Osgood f's. So I want to construct an f which satisfies this Osgood condition, so the integral of 1 over f has to be infinite, so that means f doesn't grow too quickly, but at the same time allows the toy PDE to do something bad. So, well, I'll talk about what's actually there in a second. What I actually want to do is to construct an f that takes my x, well this. So if I start at u0 at time 0, I want the solution at time 1 to look like u0 to the k. So if k is 2, basically, which is this picture here, what I want to do in time 1, I've squared my initial data. So it's kind of clear that I can find a function that's, let's say, in L2, and if I square the function, it's not going to be an L2 anymore. And that's more or less what I just have to prove happens in a couple of slides' time. So I want to construct an f that has these nice properties, but is bad in that essentially the solution increases at this kind of rate. So, and you can make this, you can construct something that's smooth if you care, but for this talk it doesn't really matter. So I'm going to take a sequence of phi's, and essentially the next phi is raising the previous one to the power of k. And why don't I start with 0 at 0, and then 2, and then it's going to be 2 squared, 2 to the 2 to the 2, 2 to the 2 to the 2 to the 2, etc. So I can't really draw very many of those. On the picture, this is a graph of this f when k is 2. So it has these long regions where it's constant. And this is precisely enough that if x dot is equal to this, then you start off at phi I, and by time 1, you end up at phi I plus 1. So you're increasing quite quickly, just at the right amount, so that if at time 0 you start at 2, then by time 1 you're at 2 squared. And if you start at 8, then by time 1 you're at 64. So this is my nasty f. So essentially it has long periods of being constant. And the periods of being constant are long enough to ensure that you don't grow too quickly and that the integral of 1 over f is infinite. So it sits underneath x squared, which is this red line. So in general, my function, if I choose a particular k, it's going to be less than x to the k. But because essentially near phi I, it's basically phi I, or comparable to phi I, it has points where it's more or less like y equals x. So it's bounded above by s to the k, and, well, not quite bounded below, but bounded below by a constant times s. So the lower bound is nice and everything would exist in all situations in a nice way, and the upper bound is bad. So if I construct this f, I want it to be Osgood, and it is, because basically, so the integral of 1 over f, it's constant on these integrals I. The length of I is exactly phi I plus 1 minus phi I, and that's exactly the value of the function. So I'm just adding on 1 an infinite number of times. So this thing grows slowly enough that the solutions of the ODE are not going to blow up in finite time. And you can see that by this, because at time 1, you're squared. At time 2, you just square the previous thing, and you keep getting higher, but you certainly don't blow up in finite time. So solutions of the ODE, the global, and just notice that if your initial data is greater than or equal to phi I, then your solution at time t, well, f of phi I is phi I plus 1 minus phi I, and it's only increasing. So the rate of growth is at least this. So at time t, your phi I plus t times phi I plus 1 minus phi I. So essentially for small t, you're greater than or equal to t times phi I to the k. So in fact, no matter how small t is, your solution is going to be comparable to phi I to the k. So we've got a growth bound, but we don't have a similar lower bound. We've got a kind of linear lower bound. We've got global solutions, and going forward, any time t, the solution is bounded by t times phi I to the k if the initial data is bigger than phi I. So I want to get instant blow-up for the toy PDE with just introducing spatial dependence in L1. So I just want to look at the integral of something. If it's only integrable, then I can show that the integral doesn't exist for positive t. So I'm going to look for initial data, which goes by mod x to the minus alpha, so it has a singularity at 0. And if I'm in n dimensions, then I want to take alpha less than or equal to, less than n to ensure that this thing is integrable. And I cut it off. This chi-r is a cut-off, so it's 1 on a ball of radius r and 0 outside. So that ensures that my initial data is in L1, and for later on I want to make sure this alpha is also bigger than n over k. So I've got my nasty f, my nasty Osgood f, and I've taken k to be bigger than 1, and now I choose alpha bigger than n over k and less than n, and take this as my initial data. So the argument's precisely, well, essentially u of x and t is going to be t, and now I'm raising this thing to the power of k. Well, alpha k is bigger than n, so u shouldn't be integrable anymore. So I've got immediate blow-up for this toy PDE in L1. And this is just writing down the argument properly, but it's a good prototype of what's to come. So here's the initial data. The place where this initial data is bigger than phi I, so if my data is bigger than phi I know that the solution of my ODE is going to be bigger than t phi I to the k. Well, the place where this is bigger than phi I, certainly bigger than phi I when all x sufficiently small, that's what this sufficiently small means, and this is a set of measure phi I to the minus n over alpha, because it's a ball of radius r in Rn, so this is just r to the n. So my function is going to be bigger than t phi I to the k when my initial data is bigger than phi. This thing at time t is bigger than t phi I to the k, and that's true for all these small x's here. So if I try and work out the integral of u, well, it's bounded by, it's certainly bounded below by the value of u, t phi I to the k, on a set which is of measure phi I to the minus n over alpha. So that just gives me a lower bound on this, is this expression here. So if we get the t, that's always positive, and so is the c. This is true for any I. These phi i's tend to infinity, as I tends to infinity, so provided that this exponent is greater than 0, which it is when k is bigger than n over alpha, then the solution, this integral goes to infinity, and so this must be infinite, so the solution of the toy PD is blown up instantly. So even though the ODE exists for all time, I can find some initial data in L1 where the toy PD blows up immediately. And a very similar argument will show that if you take, if you're interested in data in LQ, then you can do the same thing. So you can find initial data in LQ, which means you have to take a particular choice of alpha in here, and you can still run this argument, and the U isn't in L1 for any positive T. So, I mean, in some ways this isn't really a surprise, because all you're saying is you can start here, this might be all right for bounded data, but introducing unbounded data can mess things up in this toy PDE. And the only real excuse for introducing unbounded data is because you know that the heat equation does nice things to unbounded data and smooths it out and makes it bounded. So often in this kind of, if you like, non-linear heat equation, you have the situation where you start in some LP and then you run the equation and everything turns out to be nice. So in a way, what happens with the toy PDE is unsurprising. We're only doing it because we really want to understand what happens when we introduce diffusion. So let's do that now. So first of all, let me just recall some things about the heat equation that I'm going to need to use. So we're going to look at this equation here. So essentially, I know that without the diffusion, things are bad. The diffusion is going to make things better, but I want to make sure that the way that the diffusion makes things better isn't enough to counteract what the nasty F will do. So let's just recall some things about what the heat semigroup does. So we take a solution of the heat equation. I'm now going to look on the whole space because it's very useful to be able to use this explicit form of what the heat equation does to an initial data. And I'll say something about the end about what happens if you're in a bounded domain with Dirichlet boundary conditions, which is probably a more interesting problem. It turns out that essentially the argument in the whole space works exactly the same on a bounded domain. So if we take the heat equation on the whole of Rn, then the solution, well, by the solution, I'm going to understand what you get if you plug U0 into here. So without some conditions on the decay of U0, there are nasty situations where you can have more than one solution. I want the one given explicitly by this heat semigroup. So this is essentially the convolution of the initial data with the solution starting with a delta function at y. So this gives you an explicit expression, if you like, for the solution of this equation if you start at U0. And very occasionally I might want to write it like this. So this is the integral of U0 against the kernel that depends on t and the difference between x and y. Now once you've got this, it's relatively easy to see that if you start off positive, then the solution stays positive because this k here is a positive thing. That immediately implies, because this is linear, that if the initial data is ordered, then the solutions stay ordered. A nice property that makes some of the arguments easier is that if you integrate with respect, if you integrate here with respect to x, there's no y dependent there. If you just integrate with respect to x, you can do that, and the integral of this kernel over the whole space is 1. So that tells you that if you flow something with a heat semigroup, then the L1 norm doesn't change. So that's basically the total amount of heat doesn't change, it just moves around, which is kind of what you expect physically. And finally, you have this smoothing estimate. So this is the kind of mathematical formulation of the fact that if you start off with some nasty data with a peak, and you let it diffuse, then the peak comes down and everything starts to look smooth. So, well, if you start in LS, then you end up in LR, if R is greater than S, and there's some decay back to here that tells you how quickly you smooth. So the only thing I'm going to need is, if you start in L1, so if you're just integrable, well, for every positive t you're bounded, and the rate at which you smooth is like t to the minus n over 2. So essentially, what I'm going to do now is two things. I'm going to show you that if this k, like how bad your f is, isn't too large, the diffusion is now going to save you and give you a solution that exists for all time. But if the k isn't too large, then you're still going to blow up immediately. So the positive result, essentially I need an argument for the existence of solutions to these kinds of nonlinear heat equations. So what I want is a nice way of writing the solution of this that I can do some easy analysis with. So essentially I'm going to use something called the variation of constants formula, and if you're not familiar with it, this is the kind of way to understand it. So basically I've got the heat equation here. This is an ODE, but it's like a heat equation. This is something that's like a diffusion, and this is my nonlinear term. So I multiply by an integrating factor, and I integrate, which just gives me this, and I rearrange, and it tells me x of t in terms of, well, the initial condition decays, because this is something decaying, and then I've got some integral expression, which is an interaction between the decay from the heat semigroup or from A and the nonlinear term. So if you look at this by analogy with this thing, and recall that if you like, the heat semigroup is like e to the t Laplacian, whatever that means, then any reasonable solution of this is going to satisfy this variation of constants formula. So you've got the initial data, and the effect of that is going to decay, and then here some interaction between the nonlinearity and the decay from the heat semigroup. So just as, if you like, I defined what I meant by a solution of the heat equation is something that satisfies this, I'm going to define a solution of this nonlinear heat equation precisely by something that satisfies this formula. And essentially any solution that's reasonable will satisfy this kind of variation of constants formula. So what I'm going to use is a local existence result for this equation using monotonicity ideas. So this goes back to Weissler, and McGowey did something similar in his thesis and was able to push some particular cases that Weissler hadn't been able to treat. But the argument is similar, but it's very nice. So you have a solution of this equation is given by the variation of constants formula, and a super solution is a function v that if you plug it into this variation of constants formula thing on the right-hand side, you get something less than what you started with. But if you get exactly what you started with, if you plug a u into here, it has to be a solution. So essentially you kind of find an upper bound on solutions by finding some function that you can plug in and you go down. So there's a solution if and only if there's a super solution. So essentially solving the equation boils down to trying to find a super solution for the equation, and that should be a lot easier. So you don't have to find an exact solution, you have to guess a super solution that somehow is going to bound things. And the argument's very nice. You take your super solution, and then you just iterate this function f on your super solution, and it gives you a sequence of functions that are essentially decreasing and bounded below. So if you take wn plus 1, that's f of wn. By induction, this is less than or equal to f of wn minus 1, but that's wn. So wn plus 1 is less than or equal to wn. And the induction starts because w1 is f of w0, and that's less than w0. So you can define this limit pointwise, and then because everything's given by integrals, you can use the monotone convergence theorem and get a solution. So the proof is actually very straightforward, And the method is nice because it reduces the problem of finding a solution, or at least of proving a solution exists, to dreaming up a super solution. So the slide looks kind of crazy, but the idea is that at least when our parameter k is smaller than 1 plus 2 over n, then we're going to have existence, local existence, when our initial data is in L1. So for the toy PDE, for any k greater than 1, we have immediate blow-up, and now we're adding diffusion, and it's going to save us, at least in this regime when k is less than 1 plus 2 over n. So all we have to do for initial data in L1, I'm taking it to be positive, we have to find a super solution. And the super solution is just twice what you get from the heat equation acting on phi. So our f is bounded above by s to the k, so what we need to show is that when you plug twice the heat solution acting on phi into the right-hand side of the definition of solution, we get something smaller than what we started off with. So, let me see if I can go through this quickly. This is our f. F is less than s to the k, so we replace this by this expression to the k. S is linear, and, well, so this thing is less than the maximum value of this inside bit to the k minus 1, that's here, times SS5. The heat semigroup's linear, so this factor here we can pull out, that's what's sitting here, and then we have ST minus S acting on SS5. So this is advanced by time S, this is advanced by time t minus S, so that's just advancing by time t, and now this doesn't depend on S, and you can pull it out of the integral. So in fact, we've got f of twice st5 is some number times st5. So if this number is smaller than 2, then S2 st5 is indeed a super solution. So when's this going to be smaller than 2? Well, it's going to be smaller than 2 if this integrand is integrable, because then we can make it small by taking t small, and we just use a smoothing estimate from L1 to L infinity to bound this thing here, and we end up with some exponent in here. And if this exponent is less than 1, then this is integrable, and we've got a super solution, so we have a local solution. And there's a condition, and it turns out to be k is less than 1 plus 2 over n. So I'm in a lot of too many steps, but essentially this is a standard local existence argument for ut minus Laplacian u is u to the p. And if the rate of growth of the nonlinearity isn't too large, then we get local existence. So now, so here the Laplacian has saved us in this regime. And it's a particular case of a more general result, so if we're interested in initial data in LQ, and our long linear is bounded by s to the p, we've got local solutions when p is less than 1 plus 2q over n. And in fact, these solutions are such that they become bounded immediately, and we know that if solutions are bounded, they're bounded above by solutions of the ODE, which exist for all time. So this local existence result, in fact, is giving us global existence of solutions for the PDE. So in a sense, this is the case that's not interesting. It's kind of when the PDE does what you expect. You've got diffusion, and it smooths you out and saves you. So much more interesting is what happens when we still have immediate blow-up. And essentially, we're going to try and do what we did before for the toy PDE. We just somehow have to get around the fact that the heat part is making our data nicer. So how much nicer does it make it? Well, we kind of want some bounds on the points where it doesn't make our data too nice. So in our toy PDE, we essentially looked at where is the initial data big, and then we hit it with the ODE, and it got bigger. And now we want to somehow do the same. But a priori, the dynamics of the ODE and the diffusion are all mixed up together, and we want some way of kind of tugging them apart. And luckily, we can do that. So this is the solution given by the variation of constants formula. And our initial data is positive, F is positive, and this heat semigroup preserves positivity. So this expression for the solution it's certainly bigger than what we get if we just hit the initial data with the heat semigroup, because this term is positive. So now let's plug this into this for u of s. So u of s is greater than s of s u0, and this bit we don't care about, this is positive. So in fact our solution is bigger than, let's put the heat semigroup acting on u0 in here, and then hit it with this bit outside. So now, if you integrate over the whole of Rn, the heat semigroup preserves the norm in L1. So we take the L1 norm on the left, we integrate over the whole of Rn. Let's swap these two things round. So now we're integrating over the whole of Rn, this heat semigroup attacking this thing, and that preserves the R1 norm. So we can just get rid of this. If we take the integral over the whole of Rn, we lose this part here. So now, the integral of ut is bounded below by this quantity. So now, this is a direct competition between f, which is making things worse, and the heat semigroup, which is making things nice. So if we can find points where the heat semigroup on u0 is still big, then hopefully we can hit it with f and integrate, and we'll get something that's infinite, and then we'll have blow up in L1. So the question is, where, if we start with our initial data, which is like this mod x to the minus alpha, where after time s is it bigger than some prescribed phi? So that's what I'm going to look at now. So let's write, this is the solution of the heat equation with our initial data u0. And I'm going to let m be the smallest value that it takes on a ball of radius 1 between time 0 and 1. You'll see this pops up towards the end. So then I want to convince you that w is greater than this thing here. So if I want to take this very big, I can do it, and I can do it on a ball of radius something for small time. So we've got initial data that goes like this. Where is it big after the heat equation's been acting on it? Well, it's big near the origin in this ball for a small length of time. So I just use the explicit solution of the heat equation, and I make some changes of variables, and it turns out that, so this is w, so it's radially decreasing, so its biggest value, this is an x whose modulus is 1 over psi, and for any x less, whose modulus is less than that, it will be greater than or equal to this. So I want to bound this below, and it turns out it's bounded below by this. And this w is the solution of the heat equation at x hat for this time. And this thing, by assumption, by definition, is bounded below by m. So essentially, I just manipulate the exact solution of the heat equation to give this lower bound here. So I'm going to stay greater than or equal to phi in some ball for some time. And this is like 1 over alpha, and this is time like minus 2 over alpha. So for a short time, in a small ball, I know that my solution, even after I fit it with the heat equation, is going to stay large. So I can use this to get the instant blow up I want in L1. So this is the data I'm taking. I choose the right alpha. Then this is what came from my slide before. So now I'm just looking at the integral of a small time on the whole of Rn. So the integral at time t is the integral from 0 to t. Sorry, the L1 norm at time t is bounded below by the integral from 0 to t of this expression here, which is positive. So I can certainly make the time interval shorter, and I'm going to make it smaller so that this is less than t. So then in here, I know that SSU0 is bigger than phi I on this ball. So I'm going to take the measure of this ball, and then SSU0 is bigger than phi, and if the argument here is bigger than phi, then f of that is bigger than phi I to the k, because that's how I define my f. So I can replace this by phi I to the k, and putting this all together, I get this expression here. And the argument's just what I had before. These phi i's tend to infinity as I tends to infinity. So if this exponent is positive, then in fact this norm must be infinite. And if you just fiddle around with the ranges of the alphas and n's, if k is bigger than 1 plus 2 over n, I can find an alpha where the initial data is L1, but the solution can't be an L1 for any positive t. So I'm still getting immediate blow-up even though the F would make the solution be ODE nice. And a very similar argument shows that you can do something in LQ, but then it goes a bit wrong. So what this argument does is it gives me a lower bound in L1 and shows that that has to be infinite. Now I'm on the whole space. So if you're in a bounded domain, if you know about the norm, let's say in L3, you know about the norm in L1. But on the whole space, you can have a function where if you cube it, it's integrable, but if you just take the function itself, it's not. You don't have an ordering of these LP spaces. So more or less without any additional work, you can show that there's an initial data in LQ that blows up in L1, but that's not really what we want. We want to say it also blows up in LQ. So we can do a tiny bit more and get that by doing some localization. So it's not true that blowing up in L1 would tell you that you blew up in LQ, essentially because on the whole space you don't have a Holder inequality that will order the LP space. But if you're on a bounded domain, then you do. So if you can show blow up in a ball, then that will give you a blow up of LQ norm in a ball, which certainly implies the blow up of LQ on the whole space. And if you look at what's going on in this argument, you ought to be able to, because essentially all the nasty behavior is occurring in this little ball near the origin. And the only thing we've done at some point is we've used this trick of getting rid of the heat semigroup here because the L1 norm is preserved. So can we be a bit clever and sort that out? And the answer is yes. So now here it kind of looks quite nasty, but the idea is really straightforward. So let's not look at the integral of u over the whole space. We'll look at the integral over a ball. So this is given by the heat semigroup, which you can write down explicitly. You swap the order of integration. Then you notice that this ball is small. That means basically that, sorry, here. So if you swap the order of integration, now you're integrating now over x in a ball of radius r, and y is basically 0 because this thing is small. So you certainly included in that range of integration is a ball of radius r over 2. So let's just forget the y and turn this to a ball of r over 2. Do some substitution. This factor is less than 1, so this is bigger than a ball of r over 4. This integral gives you a constant, and we get exactly what we wanted before. So we get local blow up in L1, gives us local blow up in L2, and blow up in LQ for the whole space. So, one more slide with content, and then I'll just kind of tell you again what I've said already. So you can do this with Dirichlet boundary conditions. So we have a bounded domain, we want u to be 0 on the boundary. Essentially from that last argument here, everything just depended what happened on some ball of radius r, which is where our function is nasty. So there's a nice result by Van den Berg from the 90s, which says that if you look at the kernel for the heat semigroup with Dirichlet boundary conditions, it's bounded below by something times the semigroup on the whole space. So all our arguments are basically just using the form of the semigroup on the whole space, and if we're doing Dirichlet boundary conditions and our integrals over some bounded subdomain, we can replace the Dirichlet kernel with the one for the heat semigroup on the whole space. So the result somehow says this: you get this lower bound, you take a convex subset where you can join anything by a line, and then you have this result. And there's a factor in the front which depends on how close to the boundary you are. So there's a nice kind of hand-wavy sort of idea, if you like, that the boundaries aren't important if you're far away for the solution of the heat equation. You don't feel the boundaries, certainly for a small length of time. And so you can put this together with the stuff we've already done to deal with Dirichlet boundary conditions. So let me summarize what I've said and what we know and what we don't. So the main observation is you can have properties of ordinary differential equations and they're not immediately inherited by partial differential equations. And that can be properties that are good. So we've had an Osgood F, which means that the ODE has solutions that exist for all time, and we've got immediate blow up for the PDE in these LP spaces. Contrary, Phelan, Niedermeyer, and Vasquez have an example of an Osgood F, of a non-Osgood F, so solutions of the ODE blow up in a finite time, and then by adding diffusion, the PDE does have global solutions. So you really can't just move seamlessly from one to the other. For our particular F, we had global existence of the PDE for all initial data in LQ if K was in this range, and immediate blow-up if K was in this range. So, I mean, the kind of thing that happens if you're a mathematician is once you do this, you get very bothered about what happens in the gap when K is not covered by these two Ks. So they match up if K is equal to 1. But even then you could worry about what happens if K is equal to 1 plus 2 over 1 plus 2 over n. So there's a kind of technical and kind of fun, if you like, technical question on what's actually happening for this range of K where they don't really coincide. More interestingly, for this diffusion-induced blow-up, what is really going on here, and what's the real mechanism? And is there some general theory where you can say there's a class of systems, ODE systems, where if you add diffusion, you'll get instant blow-up? And I think, essentially the theory of this is a bunch of examples. Here's an example of some ODEs that do something nice, and I'm going to add diffusion and they blow up. So it's really not clear what the mechanism there really is, and that's definitely something to be interesting to understand. And then finally, of course, what really is the relationship between the regularity for solutions of Euler and solutions of the Navier-Stokes? I mean, the ideal thing here is that somebody very clever comes up with a proof that the 3D Euler equations are regular, and then there's a much easier proof that that implies that the solutions of the Navier-Stokes equations are regular, and then you kind of snap all the $1 million prize from solving this note. And I'll stop there.
Any question or comments?
I guess from my perspective, it looks like the problem with your system is somehow there's two timescales involved, because the advection changes rapidly because it doesn't shorten periods, which are somehow shorter than the diffusive timescales, and that's what causes the issue with your system. So would you expect that some mechanism might exist in the Euler equations for that to happen? Or because your F jumps up. So you've got this growth from above, but then you've got the slope from below.
I don't know. I mean, it somehow, certainly in Navier-Stokes, what you tend to find is that it's probably the case that as you're blowing up, the kinds of bounds that you use on the solutions, the blow up then somehow imply that nice things also have to happen. So there's a kind of, that sort of switching backwards and forwards between, let me try and put it another way. There's some ways of trying to analyze various quantities where you can say, well, if things were bad, this would happen. But then if you assume that they're always bad, you can show that actually they kind of get self-regulated. So there has to be some switching between bad regions and nice regions. And depending on how the switching happens, the solutions are going to be nice or not, and it's not clear which way around.
I was going to ask you, James, in your construction of this Osgood F, the F was a discontinuous function.
It was, but you can smooth it out, it doesn't
Okay.
matter much.
Okay, this is.
So I mean, it was just going like that, and if you just put some linear interpolations, everything works. It just makes it a little bit messy.
Because later on, when you were talking about this result that connects it to sub-solutions, there F was assumed to be continuous.
Yeah. Well, in fact, but it's okay. You just need an upper bound that's continuous.
Indeed.
So anything that
so
sits
this I know
below.
you never actually use continuity.
Any more questions? I have a question about the first question in the slide. There is a way to have a response to the first question. How is the possible path to follow to understand the behavior of the system in that gap?
is there? My feeling is that the problem is that the blow-up part, which is this bad part, actually relies on showing blow-up in L1 and then kind of pushing that into L cubed. And I think that's the bit that's, my suspicion would be that this, if you're bigger than this, everything goes wrong.
Okay.
But you somehow need a direct way of dealing with the fact that you want things to blow up in L cubed. I think that's it.
Yes, thanks again, Professor Robinson.